Shall I start? Okay, so good evening, everybody. Thanks for staying. I will talk about numerical modeling of submarine landslides. Now this work is done with collaboration with Mr. Dr. Avshalom Gans from Mariel University and master student Miriam Gindis. Now, why shall we talk about submarine landslides? What is the importance? So the importance is the submarine infrastructure for oil and gas mainly, which can be subjected to the large soil movements. So it's actually probably, for now, it's the main cause, the reason to model submarine landslides. Now, the other aspect is genesis of tsunami. So submarine landslide can also cause huge tsunami waves. And it can also make some harm to the, also to the infrastructures and also to the population. Okay. So when we are talking about submarine landslides, let's say we are talking about some slope and we have some infrastructures. So here you can see some pipeline profile and we have a slope. So the first thing that the geotechnical engineer would do, he would check if slope is stable. Indeed, it's what the geotechnical engineer can do, the only thing, if it's stable. Stable, geotechnical engineer goes away. But the question is it still cost effective to place some submarine infrastructure beneath the slope? Maybe it can be some cost effective. Even if it fails, it's also possible to build here for some, okay. Now I feel better. Okay, so shall I start from the beginning? Okay. So we were talking about the slope, and we were talking what happens if it becomes unstable. So if it's still cost effective to put infrastructure beneath this slope. And actually it can be. Also, it's possible to build some kind of protection structures here that may be also cost effective. So our task now is to evaluate the impact forces on the infrastructure. So it's the main purpose. So in this case, what we have to do is to perform large deformation numerical analysis. Okay. I think it's empty. Okay. Now I feel like at home at my own university in my own class. It happens to me many times. Right now, is it better? Or this one? No, don't. I think it makes signals that we have to go to the dinner. No, this way. Okay, not yet. Okay. So let's look at the techniques for large deformation numerical analysis. So there are some techniques. There is not all the techniques that exist. So probably some of the more popular, I don't know, arbitrary Lagrangian Eulerian, smooth particle hydrodynamics, particle finite element methods, NPM. And now there is Eulerian framework. And lazy people, what they do, they choose something that you can take from commercial software, right? It's the easiest way, so we will adopt Eulerian framework within Abacus framework. Also, Professor Eugenio Onate who is actually the pioneer of PFEM, what he says actually is that it's in large-scale problems. So this method actually appears to be Eulerian framework, I say, to be more computationally efficient and robust than other approaches. So now we are blessed to use this method. Yeah, because he is actually a pioneer of PFEM. Yes, he didn't say that it's better in each context. Okay, so we use this Eulerian framework. Now what it actually does in few words, actually, it solves the balance equations. Now those balance equations can be written in some matrix form like this with a solution variable, flux function, and the source term. And now what AMOCS does, it actually performs operator split. So it splits this system into two equations. One which contains only the source term, and the second one which have this flux function. So actually the first equation, it fits the traditional Lagrangian approach that the mesh moves with the material. Actually, it's been done incrementally with small increments. So we still have no here excessive element distortions. And then in the second time, actually the second equation, the time doesn't evolve here. So we have this advective term here, and we make a geometric projection of this material to the original mesh. And we recalculate actually all the solution variables within each element, because each element here can contain two materials, or even more. In our case, it can be water with soil, or it can be water with air, soil with air. So it's actually indeed somehow three materials. So now this framework, which is adopted by AMOCS, it uses mean strain rate mixture theory. So actually it assumes that the strain rate within each element is the same for each material which comprises element. So indeed what we have is the sticking condition. It implies the sticking contact between all the elements, all the materials within the element, or particularly soil and water. So we have to take it into account somehow. And then it actually calculates the stresses according to each constitutive law for each material, and makes some volume, use also volume fraction to calculate the right percentage of each material. So actually it's the basic algorithm. There are some more advanced, but not adapted by AMOCS. Okay, so here I show you a few examples just as a tasters for what I'm going to show later. I hope it works. Yes, so you can see here some kind of landslide. I still don't talk about the triggering mechanism because it will be the next topic, that I will say. But the pictures are, the movies are okay. At least it's not something that we would not think about. Okay. Now, yes, what we have seen here, you can hear you see the shear bands actually with those colors. Those are shear bands, or in other words, it's residual plastic deformation here. So we see the plastic deformation here. Now here we actually the submarine is the landslide is submarine. So here we look at it with the water level. So here we look at velocities. Yes, we have a landslide, and we also can have here some tsunami waves. Actually, this framework can be adapted for studying the tsunamis, but the question is on which length scales. It really makes a difference. Okay, so if we look at the profile of the landslide, so we see something like this, the evolution of landslides with time. And indeed, we have here more or less all the phenomena that are believed to be in the reality, and also some phenomena that was observed in some small-scale experiments that were performed. Because when we are talking about the submarine landslides, its scale can be anything. The largest one that is recorded is a Storegga slide. It's on the order of magnitude on the whole Norway. Yes, so such experiment I don't believe that somebody can perform. It's really not a good experiment because tsunami wave will then travel around the world. But the landslide can also be on the order of meters. Yes, it can be also small. But the geologists, geomorphologists who are studying those consequences of those landslides, they really like here what they see. So we have this head, then the head is separated from the body. Also, we can see here the hydroplaning. We can see here it's the layer of water is concentrated in one element width below the sliding body. Here, also, then it's mixed with soil, and somebody called it as a shear wetting. Also, some definition by some Norwegian guy, I think, for this thing. So actually this tool can be really valuable, and if you ask what material model have you applied, the simplest linear elastic soil with strain softening here. So if we apply more advanced model, more complicated model for soil, probably we can get a better results. Okay. Now when we are talking about the real case, so here you can see some geological profile. For the example, actually what you see here, a lot of layers. Each layer has different constitutive models. There are different constitutive models on the interfaces, so it can be really a mess. So if you want to make some feasible simulation, also it's the properties of those layers. Just imagine if it's somewhere on the sea bottom, it's not so easy to get. Yes, it's a project by itself. So we want some tool, but we want some tool to at least to evaluate the possible impact forces on the infrastructure. So we can make here some assumptions. Okay, so now for the continuation of my talk, I will make some really simple case. So we put here some bedrock, which is which doesn't deform. It's some really stiff body here. So what we expect is to have here some layer of soil to fail. So actually this is called translation landslide. This long, yes, and thin. And now when we arrive at this slide, so we are talking here about the cause of the landslide. So what could be the cause of the landslide? So in general, in most cases, it's earthquake. Yes, we have earthquakes, and then we have some disasters in different places. Also, we can have here a landslide. So we can have, for example, tsunami. We can have because of the earthquake as itself, when it makes some strike slip fault to the seabed or something like this. But here we are talking about the landslide, which also may cause a tsunami, but it's triggered usually by earthquake. On the other hand, it can be a geological process or some human intervention. Now, what happens indeed after the earthquakes? The earthquakes by itself doesn't move all the soil body. Like, for example, when we are looking at some high-rise building, yes? There we have some masses, and then we we assume that each floor can move with its mass due to the earthquake in each direction. Here, the main force, driving force, is gravity. Yes. So gravity actually it wants it's applied just down, not on some side. So what happens actually? There is some place, some region below the slide where the shear strength, due to some process which we don't discuss, it can be some geochemical, I don't know, but as a result of the earthquake, some layer may become soft in it, and then the shear strength there drops to its residual value. And so this body of soil, the slope may become unstable in this case, and then it may slide down and impact the pipeline. The question now is what is this region? Yes, is it all the potential slip plane, or if it's some limited region? Yes, we can region where the shear strength dropped, which may become some stable limit, and then the earthquake this solid body will go down slope. So simply this way. So we have here some initial, for example, initial slip plane with reduced shear strength, and now this soil body starts to move downwards, and here we have shear bends. Now downhill shear bends and also some uphill shear bend with some retrogressive failure. So actually this is called catastrophic shear bend propagation. There is some progressive shear bend propagation when it's driven on it takes time, like on the large time scales, and if it's on a relatively small time scales, it's catastrophic. It's just definition of the researchers in the field. Okay, so now we'll talk a little bit about this shear bend. So shear bend usually geotechnical engineering is given as shear strength versus the displacement, yes, along the shear bend. Now, when I apply it to Abacus, to Eulerian mesh, actually there I have some failure with one element width. So we will see that it's mesh dependent, but I have to convert this law from the shear bend with kind of zero thickness to some volumetric failure. So I introduce here length scales, which its characteristic length scales, it relates to the element size. In our case, it will be the width of one element. It also depends if the mesh is structured or unstructured here for this application. And so we have here some volumetric law for this plasticity. We have here some effective strengths, which we introduce into Abacus. Now, this relation actually can be applied to all the soil, yes, because as I talked earlier, each layer can have some different models. So if we are talking about the same model, it can be applied to all the soil, but right now it's what's more important is shear bend here. Now, actually we checked how is it really working. So we made some shear test, numerical shear test. We had some box with the soil, and we apply here deformation, yes, relative deformation, and we measure the force. So if we scale it the way that I showed on the previous slide, so more or less we have the same force here, and it's kind of independent of the element size here. If we doesn't do it, we have those dotted lines. Okay, so if we look more closely into the landslide, so we have here shear bend, yes, so we have here the failed soil, and then on the tip of this shear bend we have some soil that is on the way to be fail, but we see that it's concentrated within one element width. It can be mirrored later, but on the tip it's usually within one element width. Okay, so now the question is, let's assume that we don't know about the properties so much. So we can make some soil and check what is the mass of it, just some strengths, but we don't know exactly where this initial slip plane may appear. It may appear somewhere in the bottom or somewhere in the middle of the landslide. So what we can do, we can perform some parametric study, and simply we can modify the size, the length, and the location of this initial slip plane and see which one actually brings the largest impact force, yes, on the pipeline. So, and it appears that indeed this initial location of this initial slip plane makes sense. So now I show you actually the last example. Just for comparison, we have here the same landslides. We place initial weak zone here on the left, and here we put it on the right. And then we measure the impact forces on some structure. So it's not exactly pipeline, it could be pipeline. So let's see how it evolves. Okay, so the one in the bottom, yes, we can see that there is sliding body. It's the initial slide, but then there is some secondary sliding here, yes. Actually, this pattern, it's not something same for each case. Each material property may cause some different kind of failure here. Okay, so let's see the other one. Yeah, so now we have some different failure pattern. If you see, there is some water layer beneath the structure because it's kind of plane strain simulation here, so we didn't want water to be arrested there. Okay, so we have some different soil pattern. Okay, so now let's look at them together, more or less simultaneously, what happens. Okay, so now if we compare the impact force of both cases, so we can see that evolution is a bit different. So we can have different impact force. Indeed, unfortunately, right now it's the main conclusion that it makes a difference, but some more to get some more solid conclusions, we have to investigate different types of soils, different more particular cases, just because it can be, for example, slate failure. So there I can more or less, I know which conclusion will be, but for the other, for the other types of failure, it can be something different. So it can, here we have too many things together. We have to somehow to make more narrow problems here. Okay, so now to conclude, yes, so I presented a numerical framework for the analysis of landslide impact on offshore infrastructure based on Eulerian formulation. There is some other groups in the world that work on those topics. Some guys makes really nice work with really nice approaches. But what actually I present here is more the triggering mechanism, because I don't think that somebody was talking about it. Now, Eulerian approach allows capturing various phenomena related to landslide evolution and landslide pipeline interaction. Now, different trigger mechanisms lead to different impact forces. Material parameters may affect the failure mode. So, actually, those three goes together. So parameter analysis allows to define the upper bound regardless of actual triggering mechanism and its sensitivity to various parameters. So it means actually that I don't need a geologist for the evaluation of impact forces. So they will be disappointed here, and further validation of the applied numerical approach is required here. So we are working on it. Okay, thank you.